Lotto 24 has unusual jackpot rules. The jackpot starts off at $24 and then grows $1 each day there is not a winner. If there is a winner, the jackpot returns to $24. The probability that there is a winner in a week is 0.5. This, strictly speaking, is not a normal queue because it goes down by more than one. It could go down from any number down to $24. However, by modifying the development of the steady state equations for the BSSQ, we can show that our work goes beyond typical queues and into more general Markov chains. So we'll consider this as a degenerate Bernoulli single server queuing process to determine the steady state distribution for the Lotto 24 jackpot prize. In order to do that, let's, as usual, let Q of t be the queue size, which would be the jackpot size, at time t in days. Q of t is always at least 24, and we also have that delta is equal to 1 day. So we can look at the basic two equations. So normally we have the probability of going from state I dollars, I being 24 or greater, to I plus 1 or down 1. But we won't have down 1. We'll have going all the way down to 24. So we can first look at the probability going from I to I plus 1. Well, that's the probability that there is no winner, and that's 1/2. On the other hand, the probability of going from I down to 24, whatever I is, it could have been 24, it could have been 25, it could have been 37, is the probability of a winner, and that's also 1/2. Therefore, we have by total probability that the probability that the Q in steady state at time t plus 1 is equal to I is the probability that it was in state I minus 1 and there was no winner. And so that would mean that we go from state I minus 1 to I. That would be for I is equal to 25, 26, etc. And the other part of the equation is the probability that Q at time t plus 1, i.e. one time frame into the future, is equal to 24 is 1/2. Because regardless of where we were, the probability that Q t plus 1 is equal to 24 is the probability that there was a winner at time t. And so, repeating the idea of a steady state equation from the BSSQ, we can let time go to infinity in both sides of both equations, or equivalently consider them already in steady state. The probability that Q of t plus 1 is equal to I is the same as the probability that Q of t is equal to I for all I. And so what that means is this first equation translates in steady state to pi I is equal to 1/2 pi I minus 1, for I is 25, 26, etc. And the second equation, that probability of Qt plus 1 is equal to 24 is equal to 1/2, well, this is just then pi of 24 is equal to 1/2 in steady state. So we can solve pi of 25 from the first equation with I is equal to 25 is equal to 1/2 pi of 24, but pi of 24 was 1/2, so it's 1/4. Similarly, pi of 26 is 1/2 of pi of 25, and it would be 1/8. Keep going in this way, and we find that pi of I is equal to 1/2 I to the minus 24 times pi of 24. You could recognize a pattern, or you could prove that by induction. And so this means, just by simplification, plugging the pi 24 into it, we have pi I is equal to 2 to the 23 minus I, for I is equal to 24, 25, etc. And otherwise, it's equal to 0.
Dear U of A students, while Mike has supplied the content for these videos, there is significant unpaid effort that goes into producing these videos. The folks here at Step by Step Probability are family people with young children that no longer attend school due to the COVID shutdown. Instead of spending time with our families, we made arrangements to continue producing these videos for you. In these uncertain times, it would be very encouraging to see your support through our donation button at the top of the website. Any amount is encouraging and appreciated. Please donate if you can. Thank you and keep safe.